A kettle of boiling water is a system, and everything beyond said kettle is called the surroundings. Boiling water is an example of thermochemistry. Thermochemistry relates to the branch of chemistry that involves changes in heat. A kettle of boiling water contains kinetic energy in the movement of the water molecules and potential energy in the bonds of the water molecule. The energy that increases the temperature of the water will be in the form of heat. This reaction requires an intake of energy in the form of heat rather than a release. It is for these reasons that boiling water is viewed as an endothermic reaction, one that takes in energy, rather than an exothermic reaction, which is one that releases energy.
The work of boiling water is equal to the product of the force and the distance. Work would be done if, for example, the steam from the boiling water was used to raise a piston a certain distance. This means that the greater amount of energy used boiling and the greater steam produced. The greater the amount of work is a closed system, where matter cannot be escaped. The topic of temperature. Temperature is a good example of a state function. State function is a value that is the same regardless of how one reached it. For example, the altitude of a mountain. Whether you go straight up the mountain or it takes you a half an hour, or you go zigzags up the mountain which takes you 3 hours, the altitude of the mountain summit will always stay the same. Another example is if one has a kettle of water which is heated up to 25 degrees, is then heated up to 100 degrees. The energy would be the same if one had cooled it from 25 degrees to 0 degrees, and then heated up to 100 degrees.
You can measure the total energy of a system via the use of enthalpy. Enthalpy is the change in heat during the process of a reaction. It is either a negative or a positive value, negative meaning that the reaction was endothermic, and positive meaning that the reaction was exothermic. Relevant to this is the first law of thermodynamics. This law is essentially the law of conservation of energy adapted to thermodynamics. It states that the internal energy, which is made up of a system's potential and kinetic energy, of a system must be balanced on both sides of the equation. The energy of the reactants and the products must be the same. Heated water is a relatively simple example. H2O liquid to H2O gas will have the same amount of energy on each side. Furthermore, there are a number of formulae one can remember to help in calculating enthalpy. Enthalpy itself, delta H, is equal to Q, the change in heat. This change in energy, delta E, is the sum of the heat change and the amount of work done.
To calculate enthalpy, one first needs to know the specific heat capacity of the compounds involved. The specific heat capacity is the heat capacity of a specific mass of said compound. The heat capacity shows the amount of energy required to raise 1 gram of said compound to 1 degree. To contrast, the molar heat capacity is the amount of energy required to heat 1 mole of a compound at 1 degree Celsius. Heat capacity is written as joules per Kelvin. The heat capacity of water is 4.18, for example, which means that to heat 1 gram of water, one needs 4.18 joules per gram times Kelvin. Another important feature of thermodynamics to remember is Hess's law. Hess's law states that the enthalpy change in converting reactants into products is the same regardless of the route taken. One should link this to state functions mentioned earlier. To help study Hess's law, one needs to know the enthalpy of formation. The standard enthalpy of formation is the enthalpy of 1 mole of a compound. The enthalpy of a solution, enthalpy of combustion, and enthalpy of a reaction are similar too, referring to 1 mole of an ionic solution, 1 mole of a combustion reaction, and 1 mole of a chemical reaction respectively. Again, relating to this point, a calorie with a small c relates to the amount of energy required to heat 1 gram of water at 1 degree Celsius. A kilocalorie is how much energy is required to heat a kilogram of water by 1 degree.